Alright, so in this video I'm going to show you how to do another question on moments. So we've got a plank of length 5 metres and a mass of 20 kilograms is placed on a quayside with 2 metres of the plank sticking out over the quayside. A child of mass 40 kilograms stands on the end of the plank on the quayside. A man of mass 80 kilograms walks towards the other end of the plank. How far does he get before the plank tips? So we want to, as always, start by drawing a diagram. So we've got our plank here. Let's say the quayside ends here. So that is 2 metres. And this is going to be 3 metres. It's a total of 5 metres. We've got a child of mass 40 kilograms on the end on the quayside. So if he's on the quayside, he's over here. So we'll put the child here, and we've got then the reaction from his feet acting downwards on the plank, and that has a magnitude of 40 G newtons. Okay, and of course we've also got the weight of the plank. Now the question doesn't say so, but we have to assume that this is a uniform plank because it doesn't tell us anything about where its centre of mass might be, so let's assume it's a uniform plank, which means that the weight of the plank will act exactly at its centre, so that is 0.5 metres, so that it's a total of 2.5 metres from each end, and the weight of the plank is 20 G newtons. Okay, and now we've got a man of mass 80 kilograms walks towards the other end. So we're going to assume that he starts here and he walks along. Okay, so we need to think about how far does he get before the plank tips. So if he walks along here, as long as he's on this side, he's probably still weighing it down over here. It's not going to tip until he gets probably some way over the edge. So let's say we have no idea exactly where he is, but let's say he's somewhere about here. So let's put his force acting downwards, which is going to be equal to his weight, which is 80 G. And what we want to know is what's this distance. Okay, so how far he gets, which is x. So how far does he get perhaps means all the way from the beginning here, but in terms of our calculations, it might be easier to label that distance as x to begin with, and then afterwards add on 3 metres. So if it is going to tip, it's going to tip about this point, the edge of the quayside, so the reaction force will be acting there, and it will be about to tip across like this. That's what's going to happen. It's about to tip like this. So, but if it hasn't actually tipped, it's just about to do that. That means that this system is still in equilibrium. So let's label the edge of the quayside there as A, and let's take moments about A. Okay, and I'm going to do clockwise first. So what's going to tend this to go clockwise about A? Well, just that 80 G newtons from the man, so that's going to be, the moment of that force is going to be 80 G times the distance, which we've just said is x there. And that's the only clockwise moment that we have. The R is not going to have a moment at all as it's acting through the pivot point, but we are going to have an anti-clockwise moment over here of 20 G times 0.5, and we're also going to have another anti-clockwise one over here of 40 G times 3. Okay, so just the force times the distance as always. Now we've said this is our limiting equilibrium, so this is still equal to 0. Okay. Now we want to solve this then for x. Now we can see that there's actually a g in every single term, so that's going to nicely cancel out. We don't need to worry about that. And we've got 80x equals 10 because if we move this over to the other side, it's going to be positive. So 10 plus 120. So 80x equals 130. So x is going to be 130 divided by 80, which is 1.625 meters, which means he can walk a total of 3 plus that, so 4.625 meters before it tips. Assuming that he started on this end and walked along here. It's a total of 4.625 meters.